So module 4, application of Fourier series for circuits. Module 5, application of Fourier transform for circuits. So in general, Fourier analysis that is used to transform, okay, from time domain to frequency domain. Okay. So basically, Fourier analysis that is used to transform from time domain to frequency domain. What is the basic difference between Fourier series and Fourier transform? As I stated in the previous discussion, for periodic signals, we can use Fourier series. Okay? For periodic signals, we can use Fourier series, but there are many other aperiodic or non-periodic signals like step function. Okay? So if you notice step function, it will be something like this. If you consider u of t, from 0 to infinity, it will not repeat, it will be same. It is a aperiodic signal. This is an important signal. Similarly, if you consider exponential signal, exponentially decreasing signal, this is not periodic. There are many such important signals which can be used as excitation. So, whenever you are going for aperiodic signals, you cannot use Fourier series. We need to go for Fourier transform. Okay. So again, the process is similar to phasor domain analysis, Laplace Fourier series. What we need to do? First of all, we need to transform the circuit from time domain to frequency domain. Then we need to analyze the circuit. Then finally, we need to represent the result in the time domain. If required, we will be representing the results in the time domain. Okay. So, whatever the statements we have discussed, they are available here. If you notice, the first one, a periodic non-sinusoidal signal that can be represented, okay, using Fourier series. But there are many important non-periodic functions such as unit step, exponential signals. Okay. So for that we cannot use Fourier series. So for those signals we are going for Fourier transform. Fourier transform basically transforms a time domain signal to frequency domain signal. Okay. So now we will discuss what are the equations used for Fourier transform. Okay. So again, I am going to write time domain signal f of t . Okay. Its Fourier transform pair capital F of omega. So small f time domain, capital F frequency domain. This is function of time, this is function of frequency. Okay. These two are Fourier transform pairs. So anyone remember Laplace transform expression? In Laplace transform, f of t in the time domain, f of s in the s domain. So f of s integral minus infinity to infinity, f of t e power minus st dt. Okay. What is the nature of s? What is the nature of s? Is it real or complex? S is complex. So we represented S something like this, sigma plus j omega. Okay. Suppose the real part of the S, which is sigma is 0. Then Laplace transform will become Fourier transform. Okay, substitute that here. So f of j omega or just omega. Okay, because sigma is 0. This is equal to integral minus infinity to plus infinity f of t e power, instead of s I am just writing j omega. Okay, so this is the Fourier transform equation. So it's very easy. You can, if you know the relationship in time domain and s domain relationship, what you can do, you can substitute just s equal to j omega. Okay, in the Laplace, you will get the result for Fourier. Okay, so and one more thing, we have discussed the pole 0 plot. We have taken the s plane, which is sigma and j omega. So sigma is 0 means we don't have this axis. Okay, we are operating at j omega axis. That you need to understand. Okay. So you can notice the first formula, Fourier transform, forward transform. F of omega is f of t is equal to integral minus infinity to plus infinity f of t e power minus j omega t dt. Okay. This is the forward transform. Suppose if I have the answer in frequency domain, I need to go for inverse Fourier transform to get the time domain result. So time domain, it is f of t. F of t is f inverse f of omega 1 over 2 pi, some scaling factor, integral minus infinity to plus infinity. I am going to integrate this f of omega e power. See here e power minus j omega t, here it is plus j omega t. Okay, when you transform from time domain to frequency domain, the integration is with respect to dt. Whenever you transform from frequency to time, the integration is with respect to d omega. So note on both the equations, forward Fourier transform, inverse Fourier transform. Okay. So next one, what is the sufficient condition for a signal f of t, Fourier transform for a signal f of t exists? This is the condition, integral minus infinity to plus infinity, absolute f of t dt, that should be less than infinity. If this condition is not satisfied, then Fourier transform for that aperiodic signal f of t does not exist. Okay, note on this condition. This condition is called absolutely integrable. So f of t is some signal. I am just taking absolute, then I am integrating the signal. This should be less than infinity. This is very important. If this leads to infinity, then you can tell that Fourier transform does not exist for that signal. Okay, I can give you an example. So signals and system students, what is this? T into u of t, ramp signal. F of t, let me take f of t is t into u of t. What is the Fourier transform equation? F of omega is integral minus infinity to plus infinity f of t e power minus j omega t dt. Okay, substitute this integral. Okay, I'm just writing t. What is the support for u of t? What is the support for u of t? Only for 0 to infinity u of t is 1. For minus infinity to 0 it is 0. Okay. Sorry. See, this is not required. Just a minute. So this is not required. Actually, we need to check this condition. Integral minus infinity to plus infinity absolute f of t dt. This we have to check. No need to take Fourier transform. So we can take, you just substitute this here, integral 0 to infinity t into dt. Am I right? Integrate this t square by 2, substitute the limit. What is the value? Infinity. So according to this condition, this should be less than infinity, but we are getting infinity as the answer. So Fourier transform does not exist for this ramp signal. This signal is called ramp signal. So three things we discussed: forward, okay, Fourier transform, inverse Fourier transform, then the sufficient condition for Fourier transform, okay, which is called absolutely integrable.